Lecture 23, Part 2. So in the previous part, we talked about what is a hidden Markov model. And here we are going to talk about the main tasks associated with a hidden Markov model. So the first one is called the evaluation problem. And it's basically, suppose we know the conditional probability tables already, how do we find the probability of observing an actual sequence? So why do we need that? Maybe we need it to complete a sequence, or maybe we need it to generate new sequences. And also it is a important step of actually finding out which HMM is the most likely given a sequence. So we need to find those probabilities, and it's the easiest part. And second part that's slightly harder is, given the labels, how do we go back and figure out the missing information about the hidden sequence? So suppose we observe these labels, sequence of labels, how do we go back and figuring out these hidden states? And the last one is perhaps the most interesting one and the most difficult one, is given basically a bunch of sequences, a training data with missing values of X, how do we figure out what conditional probability tables do we use? So basically it's finding the parameters. So basically here, the learning problem is basically training an HMM. And remember, we talked about how to train these Bayesian networks. It's basically just finding the conditional probability tables. You may think it's just like computing the frequency, like counting the number of things happening. It is, but the problem is we don't know some of the features, right? So we first need to figure out what are these features, and then we can use our maximum likelihood like frequency thing. We are actually going to do that, but the hard part again is figuring out the hidden sequence. So it is also related to a general collection of problems of, if you have missing data or missing features in your data set, how do you deal with that? How do you complete the data set and then do the training? So the EM algorithm, the expectation maximization algorithm, is a very general algorithm to deal with these types of problems. And we will actually use this for HMM, and also after the midterm, we'll talk about EM again for the clustering problems. Okay, so in this part of the lecture, we'll talk about the first two, but before that, I want to briefly go through how we will use the first two to actually do part 3, the training problem. So to briefly go through what I said, the EM algorithm, it's basically start with random guess. So start with initial random weights, and then we do a forward and a backward computation. So I need to explain these later. So here the description is not very clear, but basically we want to calculate, given a hidden state, what is the probability of the labels before this time point, and then we calculate what's the probability of the labels after this time point, and then combining these, we can kind of get a sequence, the count of the sequence of hidden states, and then we can use Bayes rule to update our parameter or the weights, and then we repeat until we converge. So the general framework is kind of the same, but these two steps are kind of computationally intensive, and using a Bayes rule afterwards it's just like the regular maximum likelihood thing. Again, I'll talk about the details in the third part. Let's start with the evaluation problem. So to write down what we are actually doing here, we are finding the probability of observing a particular sequence. So the sequence may be, say, 0 or 1. The second one may be 0 or 1. And the last one may be 0 or 1. So basically, we have a bunch of zeros and ones, and then we want to figure out what's the probability that this is happening, given we have some kind of hidden Markov model already. So if we look at the formulas here, it looks like a lot and it's confusing. So let's use a specific example, and I mean not that specific, but a simplified example. So we will actually go through some numerical examples in the actual lectures. Here, suppose we go back to the example of the coronavirus, and we can go back, and initially we are starting here, and then every time I can have fever or no fever. So these are the X that we cannot observe, and these are the Y that we do observe whether we have fever or not. So the fever may be caused by like not coronavirus, and it may be caused by coronavirus, and also there may be cases with coronavirus but there's no fever. So we have all four of these probabilities, and let's say if we have a sequence at time 1, I don't have a fever, and at time 2, I do have a fever. So this is our y1, this is our y2, and we want to figure out these probabilities. Suppose we know all these weights, all these conditional probabilities. So this problem seems you have seen that before. We need all the parents, so we need to add them in, and then we need to marginalize them out. You should actually know this from the previous lecture, and you should know this for the midterm. So I will do it relatively quickly here. What we want is we keep these, and we add their parents, which the parent of y1 is x1, and say it can be either 0, 1. So let's start with 0, 0. So basically, I don't have coronavirus at all, but I somehow have fever. That's the first probability. And second one is the same. And basically, I started with no, and then I get coronavirus for some reason. And next is I always had it, but I just didn't have fever the first day. And the last one is, okay, I'm doing the wrong order. I had it, and now I don't have it, so that's kind of strange state. So each of these, for all of these, we are given these probabilities, and we add them up, then we get our total probability. So how to figure out each one of them? So let's start with something like this. The first one, again, given these things, given the model, basically. So some of them are independent. Let's see. Everything given the parent, right? X1 is 0. Probability of y2 is 1 given x2 is 0. Probability of x2 is 0 given x1 is 0. And probability of x1 is 0. So basically, this is like deconstructing this probability into 4 parts, each variable given the parent. And note that we have all of these from the conditional probability table. Again, a review of last lecture. This one is called pi 0. This one is called A00, so 0 transition to 0. And this one is called B10. Now you see why I'm ordering it like this. And this one is B00. Okay, so that's basically 2 of the B's and 1 A and 1 pi. Let's see if the formula says that. Yes, so T here is 2 and 2 of these B's and 1 A multiplied by the initial pi. Okay, so now I think you can understand these formulas a little better, and we're adding up all possible combinations of these X. So here there are 4 of them in the sum. So these are all possible combinations of x. Okay, let's maybe write down the more general form. Say A, y2 is B, and x1 is C, x2 is D. Maybe to make things more challenging, let's add one extra state. So suppose I observe the data for 3 days. X1 is D, X2 is E, X3 is F. So how to write these things in general? So if you can figure out this formula, then I guess you will completely understand what the initial formula means. So here we remember we have each variable given the parent. So here we know y1 given the only parent is x1, if you go back and look at the diagram, and that probability is one of the b's, and it's called BAD. So b is y equal to a given d. So remember, a and d, they are either 0 or 1. So I'm just using the symbol a or d. And second one is y2 given x2. So it's b, b, e, b, c, f. So these are the product of bunch of b's. And next, the probability of starting with the state D again is either 0 or 1, so it's pi D, and A, we are transitioning from D to E, so this is ADE, and lastly AEF. So product of the A's starting with a pi and the product of B's. And again, if we go back to here, it's exactly what this equation says. So of course, you don't need to remember these product notations, but you should understand what is actually happening here. Okay, so now we know the general formula for these, so I'll not write down each of the 4 terms, but you can. And if you sum them up, you'll basically get this original probability that we want. So it's actually not very difficult and not very computationally intensive. Okay, now let's move on to our next problem. This part is computationally very intensive because we want to figure out what combination of these axes maximize the probability of observing these. So here what we can do is, of course, we can write this directly as P of these y's and the x divided by probability of these y's. And these are the same, so we don't actually need to worry about them. So we just need to compare which of these is the largest. We can try all possible variation of these axes. So try all combinations. But that would take very long, even if we only have like 0 and 1. And if we have more than 0 and 1, this will take a long time to compute all of these probabilities. So we are going to use some kind of trick using the fact that they are a sequence, they are forming a sequence and they are related in some special way. So we will use something called dynamic programming. So I realized that not everyone has taken 577, so you may not know what dynamic programming is. So I'll briefly talk about it, but I'll not go into a lot of detail. So in particular, that means there will be no problems related to these on the midterm. So here, the trick that we are going to use is we are going to, instead of computing the sequence of probabilities every time, so do the product every time, we will store the maximum probability at each time step and also for each state. So here, I think if you directly look at the equations, you can figure out what's going on. But briefly, this is like the probability of y1 and x1 at the same time. And these are like probability of yt and x1 until xt at the same time. And it's kind of, we already know what happens before and we're just trying to figure out the current one, which is the best one. And indeed, that's exactly what's happening. And along the way, of course, we need to keep track of which X is actually maximizing these things. And we're going to call this the policy function. And the policy function idea is actually will be useful for the second part of the course. But I will talk about this again after the midterm, obviously. And at the end, we can just use the policy function to get our X values back. So if you don't know what dynamic programming is, you probably don't understand what I just said. So let me give an example, and hopefully after the example, you understand what we're doing. So here we start with the start. So x1 can be 0 or 1. That's our first state. We don't know yet. And x2 can also be 0, 1, x3, 0, 1. Suppose we have a sequence of only 4 values. What we will do is we will figure out the probability of y1. Y1 note that is given already. We observe this in the training set. And each of the x1 at the same time, we figure out those probabilities, and we store these probabilities as our value function at time 1. So in particular, we'll have one value for this and one value for this. So that's not the interesting part. The interesting part is the next one. Next one, we're going to figure out the probability of y2, y1, x1, and x2. So here, what we're going to use is we already know these probabilities. So what we only need to add is whether we want to go from here, from x1 being 0 state or x1 being 1 state to x2 being state 0. So suppose we want to figure out the probability here. In particular, it means we have x2 is 0 and y1, y2 we already know as from the training data, and x1 we don't know, but we want to compare which one is best. So what we'll do is we'll try this path, and we'll also try this path, and we will select the one that's the more probable one, right? Because we can compute both of these probabilities, and let's select one that's more probable, say that one. So I will keep the value of only this path. I don't care about the other one because it has a smaller probability, so it's less likely. I'll store the information in V2. And similarly, we will do the same thing for the other state. So here we have x2 is 1, and we'll try to compare going this path or going the other path like that. So maybe we want to go to the other path completely, but let's suppose we're having the same, let's use another color, here and then here. So maybe that maximizes the probability, and we will store that in V2 as well. So remember, V2 is V2 0 and V2 1. We store both of these maximal probabilities of like basically some path, and we end up at the current state at the current time. So now the interesting thing that's happening here is when we are here, we don't really care about like all the previous paths. What we care is whether we want to go in from 0 to 0 or from 1 to 0. So in particular, we only need to compare whether we want to go the purple path 0, 0, 0 or the green path 0, 1, 0. So we only need to compare these two. And one important thing is we don't need to compare it with 1, 0, 0 or 1, 1, 0. So we saved the computation for trying like all 4 possible paths that lead to x3. We only need to try 2 of them. And let's say, suppose we have this is the better one, so this leads to the higher probability. So we will store this as v30. And remember, we stored the path in the policy function as well. So basically, which state lead to this state, basically 0 here. And we do the same thing for the state 1. And it can save half of the computation again. So now suppose we are comparing the purple path 0, 0, 1, or the green path 0, 1, 1. And let's suppose the green path is a bit better. Then we have our, say, the optimal path so far are these green paths and the purple path. So I guess you see what's happening now. And so at time 4, we are going to only compare purple path to 0 or green path to 0. And so suppose we want the purple path because it has a higher probability. And for the last one, we are comparing, let's use a different color, the purple path to 1 and the green path to 1. Maybe we also want the purple path. That's also possible as well. So at this time, it feels like we wasted the time computing the green path, but well, it's small relative to like we have to try so many different paths when we hit time 4. So we already saved a lot of computation. So some of them will be wasted because some of them will never be used in the future, but it's okay. So at this stage, we cannot call them purple path and green path anymore. We need a new name. So maybe we need orange path. Again, the orange path is same as the purple, but it branches off like at time 4. So we basically keep doing this, and we keep track of the optimal path. And at the end, suppose we are at the end already. So suppose there are only 4 states. At the end, we figure out whether this is more likely or this is more likely. And then what we'll do, suppose this is more likely, we'll just backtrack this orange path to get the sequence. Sequence is basically 0, 0, 0, 1. So now we get our most likely sequence given we observe these y's already. So if you look back now at these formulas, hopefully it makes more sense. And so these ones, the way to compute these things is actually the same as what I did before for the evaluation problem. So you should spend some time to figure out why like this probability is corresponding to b multiplied by pi, and these are corresponding to b times a times the previous time probabilities, but they are again they are the same as what we did before in the previous lecture and in the previous part. So, but the main interesting part is we are keeping track of the optimal path so far to save computation, and that's basically the main idea of dynamic programming.